I'm in SPSS and I'm going to have a look at the cholesterol data with a more advanced model. Now, if you're watching this video, then I hope you're comfortable with the simple model where we just included two variables together, because this one is going to get a little bit more complicated. We're going to go back into Analyze, General Linear Model, I clicked Multivariate, I don't want that. Analyze, General Linear Model, Univariate. So I've got my simple model that I started with, and now I'm going to add in my other variables. So I also had gender as a factor, so I'm going to add that in. And I had age as a covariate, so I'm going to add that in too. Now I need to go into my model, and I'm going to just select everything and pop it in as main effects. Now I've got two categorical variables, and I might be interested in if there's any interaction between them. So for abdominal fat and gender, I might want to know, does having greater abdominal fat have more of an impact on one gender rather than another? If level of abdominal fat has the same impact on both genders, then we will see it here with the main effect. If it has a different effect for the two genders, say it affects men a lot more than it affects women, then we need another term to account for that. So we select abdominal fat and gender. We want to look at the interaction and add that in. Now, just a word of warning, every time you add in another term to your model, you need more data to be able to calculate the p-values. If you have a lot of categorical variables, it takes a lot of data to analyze it, and you may not be able to include all the interaction terms, depending on how much data you've collected. So if that happens, then start with a main effects model where you don't look at any interaction terms, and then you might have to add in the interaction terms one at a time and see if they are significant, and then take them out again if they're not, because you may not have the power in the model to run it with all of the interaction terms to start with. So I'm starting with all of the terms in the model in this case, and I'm going to remove them if they're not significant. Contrasts, I'm going to take these out because I don't want all the output. Are they both at none? They are. Plots. Now, we didn't do this in the simple one, and that's because we only had one factor. Now that we've got two factors, I want to look at this possible interaction between them. Now, it can take a little bit of fiddling around to work out what's the best way to draw these plots, and sometimes it's easier just to draw them both ways and then to see which one is giving you the best visual description of what's going on. So I might try putting in ab-fat for the horizontal and gender for the separate lines and add that in as a plot. And then I might try doing it the other way, gender on the horizontal axis and ab-fat for the separate lines and add that in as another plot. Now I will save my unstandardized predicted values and my standardized residuals. Means for, let's have a look at these. These will be easier to see on the plot, but let's get out the numbers in case we want them. So in one of the papers that we looked at, I think they had estimates of effect size. So if you want to go into some more advanced analysis, you could have a look at that, but this is okay for now. And we don't need that. Okay. So what we have is a description of our categorical variables. Now you need to check this box just in case you've done something wrong. If you accidentally include a continuous variable as a factor, so if you included weight as a factor, you would see it listed up here, and it would have a different level for every single observation, unless you had two observations which were exactly the same. And so if this box looks overwhelmingly big, it probably means you've included a variable the wrong way. Then in the next box, this is where we have all the interesting things. So we have a p-value for each hypothesis about each variable. So we have the null hypothesis for ab-fat is that there is no difference between the groups, and we've got strong evidence against that. The hypothesis for weight is that there is no relationship between weight and cholesterol, and we've got strong evidence for that. The hypothesis for gender is that there is no difference in cholesterol between the genders. With everything else, all of these hypotheses are given that everything else is included in the model. strong evidence against that. Age. Now we have a very high p-value here, so we have absolutely no evidence that age is an important predictor of cholesterol when we have already accounted for all these other variables. Now, if we ran a regression of cholesterol versus age just by itself, it may turn out to be significant, and that's because we haven't accounted for the other variables. But with the weight in there, it's not important. And then we have an interaction term which is telling us that there is a different effect of abdominal fat for the different genders. The null hypothesis is that the effect of abdominal fat is the same over the genders. So the null hypothesis for each of these is that there is either no relationship or no difference given that the other variables are in the model. We have an R-squared adjusted of about 95%, 0.948, which is really, really high. So it means we are explaining about 95% of the variation in our data with this model. Here we have our estimated marginal means for abdominal fat. Just ignore the pairwise comparisons, I think. And then again for gender. So we've looked at the abdominal fat before, and as the abdominal fat goes up, the mean for cholesterol also goes up. Now with genders, we've got a smaller difference, but on average the males are having a higher level than females. Now this is where you need to choose. This is where we did the plot two ways, one with ab fat on the horizontal axis with the separate lines for gender. This is probably the best way to do it. It makes more sense having one line connecting up all the female averages rather than this way. Sometimes it's interesting to look at them both, but let's have a look at it this way. And we can see that for females, which is in blue, as the abdominal fat goes up, we are getting an increase in cholesterol, but it's not as big as the increase as males are getting. So the males have actually started off a little bit lower, but with some abdominal fat they've shot right up, and then they've gone up even higher with severe abdominal fat. So this is saying that abdominal fat is having more of an effect on the males than it is on the females, and this is the interaction. And this is significant as tested by this p-value here, ab fat times gender. The times does not actually mean multiplied by, it means ab fat interacted with gender. And the null hypothesis is that there's no interaction, and this is telling us that we've got strong evidence against that and there is an interaction there. So we've got this model, just about everything significant. We could run it again, taking out the age because that is not important. However, I'll let you do that by yourself. What I do want to look at is these residuals. So I'm going to say full model predicted and full model, I'll leave it at Z because it's shorter, standardize residuals. Now we can do our charts. We'll do a histogram first and check to see if it looks normal for our residuals. Full model, that's what we're looking at. Put in the normal curve. And that's looking a bit more normal now. And we're going to have a look at the residuals across the range of the predicted values. So we want the predicted values down on the x-axis and the residuals on the y-axis. And we can put a line in at 0 because the residuals should be around 0, which they will be. It's just this will help you if you're looking for any. It actually looks like there's a bit of a curve there, doesn't it? Possible. So something else you can do when you've got more than one covariate in the model, so this is when you've got more than one continuous variable in the model, sometimes you need to look at these residuals against each of those covariates to see if there's any curvature. So we can do this graph again, and instead of looking at the predicted values, we could do it against weight. And that looks fairly scattered about. So we would be interested in increasing variance. I don't know if we've got enough data at the low end to say that the variance is increasing in this case. It's possible. Certainly doesn't look like there's a curve there, which is what I was looking at that for. Take that out. Now I'm not really too interested in age because that wasn't a significant predictor anyway, and I'm going to take it out of the model. Just for the sake of argument, let's do that. And that actually looks quite random as well. And the other plots that you can do would be a PP or a QQ plot for looking at normality we looked at in regression, and we can also look at the residuals in order of the observations, which we did in the regression too, so I'll let you do that. And so you can also go through and run the whole model again, taking out the age because that wasn't significant. I'm just scrolling up for our model here. So you can run the model again, taking age out. Every time you take something out of the model or put it back into the model, the p-values can change. So you need to do these one at a time. If you want to take something out of your model, just take out the one with the highest p-value or the one you think is the least important first. And then just check what the p-values are doing and seeing if anything has changed. And then if you need to, you can take out more, or then you can look at adding in interaction terms if you didn't have enough data to add them all in to start with.